So thank you for coming. Today we have the pleasure of having Sharon visiting us. She was in Gold Coast for IEEE conference. She's an alumnus, I don't know what's the word.
She's not one now.
Alumna, but yeah, that's alumna, yes, that's Latin. Alumna of the University of Minnesota. Did you have any class with David?
Yeah.
Did you pass?
Marginally.
Marginally.
The first
Yeah,
one.
yes.
Yeah, we co-authored a paper.
Yes, co-authored the paper, so yes.
Two.
You forgot one, okay. Others, how many papers do you have in daily? One, just one, okay. But to become a professor, you need two athletes. She's at University of Columbia in New York. She works on a variety of topics. She's also the editorial board of part B, C, and transportation science. And yeah, the floor is yours.
Thank you. So it's a great pleasure to be here, especially my old professor also in the classroom. So actually you can see I changed my topic because I took suddenly it occurred to me, I took a course in Professor David Levin's class on network modeling on graph. So I think I decided to switch topic, which hopefully is more relevant. But because the mean field game approach actually connects also traffic flow with network modeling. So I hope it can maybe connect the people from different backgrounds. Okay, so I direct my lab called Detect. So basically data and innovative technology driven transportation lab at Columbia. And so far I've been there 9 years, but I'm still the only faculty in transportation, like specifically in transportation engineering. That's why it forced me to collaborate with people outside. So for example, I work with different professors in medical school. One is the ongoing project, which is the crowd management in a public transit system preparing for future pandemics. Because during pandemic, the ridership in public transit system across the world significantly dropped. So people are scared of getting tracked by the COVID viruses. So that's why we want to build some model to understand what's the real risk of taking transit when there's this kind of respiratory viruses. And on the right hand side, we also build virtual reality system to basically navigate people through complex transit system like New York City. If you are the first time visit there, taking the subway system, especially mostly underground, it can be very confusing. So we hope we can train the new users to first navigate through the VR environment and get more familiar with that. And then another interesting work I've done with a different professor in medical school is on early detection of dementia using driving data. So there was a time before COVID that the NIH in US was very interested in early detection of dementia using this kind of mobility data. So my collaborator collected 3,000 drivers' 5-year driving data. The time when they were enrolled, they were about 65. So after 5 years, most of them were already like seniors. So, and 64 of them developed early cognitive decline symptoms. So we try to build some regression model to understand this correlation. And also my group is interested in how we can incorporate so-called physics knowledge into machine learning to guide the training of machine learning. So here is just a single animation to demonstrate how we can leverage our idea of what the fundamental diagram look like to guide the training of a shallow neural network to fit this shape of fundamental diagram across these noisy data sets. And the physical knowledge we have to apply including regular radius. So normally this is a free flow, it's easier to fit. But for this part, it's because it's a patch of data. So we have to tell neural network, okay, the line don't go up because that's what the neural network try to do. They try to overfit all these different points. And so it has to be a convex curve, and also it has to fit this line is a zero basic flex when then that's where we can determine the GenAI. So the basic physics knowledge is very important in training and guiding the training. Our recent work is because everyone using GenAI nowadays, we also apply large language model, vision language model to try to generate new data. One application is the new driving video data for hopefully to train autonomous drivers to handle these different extreme scenarios. We just gave a normal driving video, and then we can add all these different fog, rain, or suburb, these different environments to the video, so that we can have more corner cases. So yeah, overall, we try to build a digital twin to basically simulate all these different aspects of transportation. And one thing I also want to mention, because Columbia has a quite strong law school, so we also work with law professors, including some professors from Germany in law and economics, trying to understand legal implication of self-driving. Basically for car, self-driving car is a human driver, so who should be liable? So how do we apportion the loss and risk among it? So, but today I want to more focus on how we use game theory to model this so-called network multi-agent systems. So this has also a lot of broad applications. For example, like the network of flights, and also Internet of Things. Sensors, they form also a network, they can even communicate. And also the ride sharing apps, right, that connect the riders, drivers, and even the network of neurons in the brain. So all these can be treated as multi-agent systems. So I see some of the things you guys also working on in this direction, or?
Actually, I'm organizing through Arman for a demo. You have some interesting robot cars downstairs for Francesco and you.
Oh.
So we try to. Can you check your phone? Yes. I just had that idea that we can show you our
Okay.
physical environment. We are working on actually communication-free algorithms for AVs, and we try to implement that with the robot cars that I showed you. So I'm just asking them that if we can do a demo after 4 p.m.
Like
Can you
also,
check the phone? Yeah, thank you.
it's also multi-agent system, yeah. So, so this kind of application not only exists in your human worlds, but also in like social worlds. We have flocking, herding behavior of birds, etc. The classical approach that people normally use is, for example, each agent, so they follow this dynamics represented by ordinary differential equations, but their dynamics are coupled, right? So one dynamic may impact the other and vice versa. They have to coordinate it to form certain. So that's what the classical ODE control system would apply. But in my talk, I would more focus on game theory approach. So there's no right or wrong or who's better or not. It's just different perspective on this modeling of multi-agent systems. So, but I would really want to promote why game theory is important by showing this video. So this is a video clip I've loaded by someone to Twitter. So captured from this person's dashboard. While he's driving either in California or like Phoenix, we don't know exactly.
What highway is that?
Hard to tell.
Railroad, Chandler.
Right, that's probably Phoenix.
Phoenix, oh, we see. So that is a Waymo car, right? You can see it has the left turning blinker on. So basically, which means that car is trying to merge to the mainland highway. But every other human drivers were able to do that except the Waymo. So Waymo had to get off from the next. So we think from humans' perspective, this is a very simple maneuver, but Waymo couldn't do it. There are multiple reasons, and let's say potential reasons we can only guess, right? So either they see the gaps, but they just don't know. They are not sure whether it's too enough for them to squeeze in. And then humans also have their own behavior reaction. They don't care because they see it's a 360-degree LiDAR. They know it's a self-driving. It's not their peers who's driving. And then also they may now be proactive, saying, okay, if I don't squeeze in, I have to get off. So what should I do? What should I do? Normally, even a conservative driver would convert it to aggressive and try to force it, but apparently Waymo doesn't have this behavior. So my point is, in the future, probably self-driving car will be programmed by manufacturer, by software designers, and they could be goal-seeking. So can we just program them by assigning some objective function, which is a trade-off between efficiency and safety? So nowadays, the companies are too worried about safety. They prioritize this. That's why it loses a lot of efficiency, of course, because they try to get high IPO. They don't want to screw up things to show bad news on highlight every day. And there's also not a clear regulation and also the law or insurance scheme for self-driving cars. So that's why safety is not the priority, but in the future, if we can program more flexible way, can we do more trade-off between these terms? And so this is the framework we try to propose. Okay, so can we just use game theory to model such kind of control of so-called many autonomous vehicles, and then even characterize the traffic flow pattern when every car is replaced by self-driving? And so this is our setup. Assume we just start with simply the setting, which is the ring road. So every car here is a AVIX autonomous car. So they are moving counterclockwise. And let's look at the green car N. And we characterize their state by Xn, so position, and Vn is their control, the velocity car N. So Vn is basically the derivative of this position. And we also assume each car try to optimize their objective function, which is J. So car N's objective also depend on all other cars. So we assume total number of cars we try to control is big N. And then the cost can consist of two terms. One is the cost function, which is time dependent. So that's why we have to integrate over entire planning horizon. The cost function can be any term. It can be running cost. So if car run too fast, there's an energy consumption and congestion, safety, and even emission. So we don't consider emission at this point. And then VT is a terminal cost. Basically, at the end of the planning horizon, what cost we want the car to achieve. So in green road here, it's simple. So basically, we just assume all their terminal costs are there, which means they don't have any preference by the end of the time big T. That's why they can be anywhere. So it's not like they have to go to reach a destination like in network. But later I will expand it to a network setting. And the objective is to solve the optimal control for car N. But if every car is doing so, then we end up with the equilibrium. So here we use the Nash equilibrium concept. The definition is that if we held all other cars velocity control fixed, so then at the equilibrium, the strategy, so its cost should be minimized or optimized. So if there's only two cars, we'll call it a differential gain because each car will solve optimal control. So their dynamics follow this ODE system, they have objectives, so it's optimal control. But if there are many cars, so this problem become not scalable. So it become a large system of all the with also optimal control objectives. So that's why we decided to borrow the concept called the mean field gain. So mean field gain, by applying the mean field approximation, we can actually control many cars. And accidentally we discover this can be kind of new traffic flow theory for self-driving cars. I will show you later on why we make that claim. We were very cautious to make that claim when we published our first paper on this. So what is mean field gain? So it's a decision-making process for multi-agent system. It's designed for the dynamic system, so which means every agent try to solve a dynamic optimal control problem. And it's a non-cooperative Nash game. So if they play a cooperative game, we call the mean field control, not the game. And it's a limit, so it assumes the number of players go to infinity. So we have to take this limit to let the n go to infinity. Okay? So since it's an introduction by these two teams independently, so this is a team in Canada, basically belong to control component. So this is from Paris. They are more like I think finance or with mathematicians. So they proposed this concept independently, and then since 2006 or 7, this mean field game was widely applied to explain all these different phenomena, including Mexican wave fishes. One thing we found it's very useful because it actually bridges the two levels, two skills. One is the microscopic agent dynamics to the macroscopic population mass. So in my talk, I will first set up how we apply mean field gain to the autonomous driving control, and also then we will extend it to network. So then on network, car not only just how to optimize speed, but also optimize the routing in there. So then we will talk about some solution algorithm. Probably we don't have too much time, but I will give you a high-level idea how we apply so-called online learning to solve this game, and some open questions. So how did we apply mean field approximation in this case? So just to give you a very hand-waving idea. So if we let the number of cars in the system go to infinity, so the cost function you can see it's changed. It now doesn't see other cars action or state. Instead you see rho is the traffic density. V is this car's own control or strategy. And this car is now we don't set it or index it by n. So it become a anonymous agent. So we don't have any index. We call it a representative player. So this player has its speed control at time t, and then also the population density, which is rho at x location x and time t. And this car doesn't see individual car anymore. It only see the population, so aggregate mass in its middle. So that's when the mean field approximation makes this the difference. And we don't solve Nash equilibrium anymore. Instead, we solve so-called mean field equilibrium. So mean field equilibrium consists of two fields. One's the U is the velocity in x and t. We call it velocity field, and traffic density field in position x and t. So how this equilibrium can be characterized? And so remember, I mentioned mean field gain can bridge from agent dynamic to the population. So to characterize this mean field equilibrium, we can first formulate an agent dynamic equation using so-called HJB equation. It's also a PDE system, so partial differential equation. But you can see the C here is the cost function defined for optimal control, and U is the optimal cost we need to solve to minimize this. So V here is the so-called value function. If you use reinforcement learning, so that's exactly the value function that we use the V value function at time t. So once we solve this HJB, we can actually, assuming we know traffic density rho, so then we can solve this one. At the dimensions in x and t. So once we have the velocity field, we can fit it into another partial differential equation, which represents the path segment. Normally they call it FTK equation, but in our context, it's just the transport equation or flow convolution equation. So rho partial t times rho times u partial x. There, we assume there's no source of the term. That's why flow is conserved. So once you fit u here, you can see, then you can solve rho. Once you solve rho, you feed it back to solve given the rho, what's the optimal rho. So this process is go iterative. If it converges, and if this is one unique mean field equilibrium, so then this actually gives us the equilibrium solution. So you can see basically mean field equilibrium is characterized by a backward PDE as a forward. So that's and then they have to solve iterative, get a fixed point. That's where the challenges always solve them. But before solving it, let me just show you demonstrate, okay, why do we care about this scheme? What's the advantage? And so we compare the mean field gain-based control versus the traffic flow-based control. Here we just use the simplest traffic flow model, LWR model, versus the other model. And then the bottom, basically this is the X space. So it's a range of values unfolded. So then 0 equal to 1. So that's why it has a periodic boundary condition. And then the blue line is the density. So the red dashed line is the velocity. So I will show you an animation of how these two quantities evolve as time goes on. And then on top, so we show you basically discretize the control and try to show you how individual curve evolves based on this design control. You can see at time t0, they start exactly at the same location every car. So they have the same initial density. So all the cars distributed and follow the same distribution in space. So for the LWR based control, so you can see there's a shock first appear and gradually it will disappear, which correspond to the top is every car when they hit the half left point, they have to slow down and all of a sudden and then speed up. However, for this mean field gain based control, so they can these two quantities can converge to uniform operation. So which means eventually every car has the same speed and same headway from the previous cars. So the question is, so what makes these two control strategies so different?
So the U were different if I mean at time t equal to 0.
0 is different. Yes, a good observation. I will come back to that, why that's the case. Yeah. So yeah, what made that different? Even at the time when t equal to 0, even given the same rho, so the U is different. So yeah, here you can see, yeah, the same rho profile, but the U is different. So LWR, and just okay, so I assume because everyone in the room probably know LWR, so I didn't say write it clearly. So the rho t, so that the top PDE, so the conservation equation, right? So that big U is the fundamental diagram. So it represents basically a mapping from density to speed. So in LWR here we use green shields. So then it is reduced to a scalar PDE equation. And then based on that, we are motivated to reinterpret LWR, which is a PDE, into a game theory by artificially design a cost function on the right hand side, which is big U minus the control. Small little u is the control strategy in time and t and x. The difference, here is a constant, which is the maximum speed, so speed limit. So if you minimize that cost function using the mean field gain scheme, you actually end up with the LWRs. The reason is very simple, because that's what the LWR actually want. It's the speed u is equal to the big. Okay. So then we interpret LWR as a mean field gain so that we can design another mean field gain for in parallel comparison. Inspired by this formulation cost in LWR, we add another cost, which is this one, the second term. The rho j is the jam density. So we try to maximize the gap between the current density from the jam density. Means that we want the representative player to avoid it. So that's the additional term we add. That makes the difference how this traffic pattern evolves, just by adding that term. So that's why we first found out that LWR actually is a special type of mean field gain. So when we propose this scheme, we are now trying to say this, we are proposing a totally new independent scheme. Actually, the existing classical traffic flow model is part of this scheme theoretical framework. Basically, we can, LWR is a one type of mean field gain with a special family of cost function that aim to steer the optimal controls velocity towards the equilibrium speed defined by the function. And second, LWR actually is a myopic mean field gain, which means that's this is kind of explain why the speed is curve is different. Because for LWR, so this rho and the u you can see is completely opposite, right? So if rho, we choose the maximum value for rho and u as 1, so this u actually equal to 1 minus 1, which means when the rho is high, the u is low. When rho is low, which is it's very sparse traffic, then the u is high. So it's totally my own decision. But here for mean field gain, it's hard to tell the direct mapping, because this U curve is determined by the entire density profile for the entire plan. So that's why we cannot. So every time I present, people ask me what's the fundamental diagram look like for mean field gain. So there's no such effect, because it's a more higher dimensional mapping from density. It's not one-to-one mapping, like we fix x and t, then rho and u count is more like u is equal to 1 minus relation.
The mapping, does it require future looking or
Future,
in time and space?
yes. So yeah, this is something about the game theory. So yeah, for example, so these are the black dots actually are the mapping. If we try to plot traffic density and flags to 1, you can see it's very messy, because it's not 1-to-1. But the LWR mapping between rho and u is just 1. The equilibrium speed and density. And so the reason is so basically this u is determined by the entire profile. That's because when we try to solve the equilibrium, we are looking at the entire planning rather from 0 to t. And when we solve the velocity profile, you have to depend on the entire. Yeah, so that's why Nash equilibrium is not easy to solve. It probably is not very realistic in this sense. But later on, I will propose how we can use the online learning scheme to solve it. Any other questions?
I have a couple, but maybe you are coming there later. So far, you're looking at the theory at homogeneous sections. Yeah.
Yes,
So-
yes. Homogeneous, you mean for all the cars, all the agents?
Meaning that there are no interruption in the flow, for example, ramps, off ramps.
Oh,
What we look right now is the way you are showing that the LWR is a special case of MFG. But then, of course, this is considering the conservation of vehicle in a closed system,
Yes.
not with entry or exiting
No.
flows, neither in infrastructure changes like speed changes, traffic lights, etc. This is for so far not considered in.
So, yeah,
Research.
for this conclusion, actually, it works in general. So I just demonstrated using this closed system. But LWR is a special piece of MFG in any scenarios because they only differ in a cost function. Yeah, you can still apply them to different these on-ramps, off-ramps, something. It's just becoming so it's very hard, so we haven't applied to all these different.
Okay.
Any other question? Then maybe let me move on to this network setting. So if we have one self-driving car, right? So we not only have to determine how fast they drive on each link segment, but when they reach a junction point, which next go to link it. So, and if we have multiple cars, so then this become similar setting the differential gain for the fleet of the self-driving. So this will become a problem when the Waymo robot taxi or other companies try to expand their services across the US. Actually recently even moved to New York City streets. But in other cities, they allow driverless car. But in New York City, now it's still required safety driver safe to observe and control the situation. How do we model route choice in this setup? So it's very like the so-called the dynamic user equilibrium idea. So assume we have a subset network. And for this one segment from node K to J, we already done it in my first part. You can use infill gain to solve how fast it drives. But when this car reaches the node I, we have to introduce additional variable, which is a beta. Beta is at time t. When this car reaches the node I at time t and its destination is D. So what's the probability that it will choose J as its next go to D? So that's what beta means. In game theory called mixed strategy, which means beta is not 0 or 1. It's just some real number between 0 and 1. But the sum of the whole together should be 1. If the beta is greater than 0, which means there's a probability ij will be selected by this car reaching node I at time t, then it implies some optimality condition. Here, what is pi? If it's equal to 0, then this cost pi d should be less. So yeah, what is pi? Pi actually you can treat it as a potential from I to D or optimal cost. If a car has to drive from I to destination, so that's the optimal cost. Similar to pi JD. But you can see they differ by a tau. Tau is the travel time when this car agent move from I to J. So that's the travel time. And then there's a difference, which is the traversing time of link IJ at time t. So it's basically determined by the cost function we define to the part. It can be any cost we want to consider running pedestrian. But when the probability is greater than 0, which means this optimality condition can be preserved. So we also consider queuing, right? So on a network, when this green car reached, there's already some car in front of it. So how do you model this queuing process? So what we did, we assume there's a point queue at each node. So cars, when they queue up, they don't occupy space, but they have to wait there. So we introduce so-called queue size at the node I at time t. So if this queue, when the green car reach, but there's a queue in front, so then we have to certify this another ODE system, which means the change of queuing rate is equal to the inflow minus capacitor. If there's a queue, then it had to be the once it's saturated, it's inflow minus. And also travel, so top other than travel time, we have to add up another queuing rate. Normally queuing delay should be proportional to the queuing size. So here we use queue size divided by. Similar here, we have to add some queuing costs. There's, we talk about when the car, right? So when we solve the speed control, when the car move on this link. And now there's also the node. When at node, we have to solve some optimality condition to choose the next node. So there are some. So these two problems are coupled. But how are they coupled? So if you remember, we define optimal cost V when the car moves on link segment. So this car, the optimal cost defined relative to this link segment should be equal to the optimal cost from node I to its destination. So this is how the link and node is coupled. Similar for node and link. So once this car leaves the node I and jump to the link ij, so its optimal cost from I to D should be minimum of the optimal cost that it take between the downstream link segments. So this is how we couple these two mean field gain modeling. One for link segment, one for node. The formulation very complicated. I don't want to write it here because it doesn't show anything interesting. But what I want to show is the maybe some results on a simplest network, the Breeze network. We always start with when we work on network modeling. So we have 4 nodes and 5 links, and we assume there are 2 origin nodes, 1 and 2, and 1 destination nodes, which is 4. So all the parts coming from node 1 and 2 try to go to node 4. And we define some running costs and even queuing data here. And then we'll compare how the traffic density and velocity evolves. And time goes on along the specific paths. Here is from node 1 to 3 to 4. So you can see there are 2 segments. On the y-axis, 1, 3, 3, 4 represents the density and velocity on these 2 segments. This is under LWR control. So how rho and U evolves. This is for mean field gain. So similarly, we use different cost function for these two. I want you to draw attention to the peak or the valley in the LWR heat map. That's when the 2 traffic streams meet each other and node 3. So you can see at LWR, because they are myopic control strategy, which means car first will speed up to reach node 3. And similarly, they happen to meet the traffic stream coming from 2. That's why they all have to slow down at node 3 and then speed up again, tidy. However, mean field gain has this, they call it anticipating. So because the control depends on future density, so that's why they can anticipate in the future I might meet the people crowds in node 3. So why don't I just slow down earlier? So you can treat it also like a departure time choice. I may depart later or wait somewhere so that I can let the crowd pass the node 3, then I will. So it's basically we call it slow, fast and slow is fast. So this is what the mean field gain can do, is anticipate what's the future traffic is like and then adjust its current control strategy. However, So because of this anticipation behavior, actually it's not easy to solve mean-field game. And the challenges in the coupling of the forward and the backward PD systems. So let me list a few methods that people use. The first is they convert to a variational game. So it's like when we solve static game, right? We can also use a potential game to solve the equilibrium. The second is the fixed point iteration, like what I said. You solve the backward, get the row, then you solve the forward with row, then you do this back and forth, and hopefully it can converge and converge to a fixed point. So there's also Newton method. So basically, you convert everything to a huge. You use both t and x. You unfold them, and then you have a big equation system to solve. And this is what we use when we publish our first paper, but we found it's not scalable. So later on, actually, since this paper came out to 2019, then people start using learning methods for some mean-field game. So at the beginning it's very simple. Because for the backward PDE, it's like solving reinforcement learning if you treat it like indiscrete. Then people just first apply reinforcement learning to solve the backward HJB equation, then plug into the forward equation and do the backwards fixed point. But we found out that it's not too much difference from the solving a MDP. So later on, let me first, maybe before I present our method, I show you how this fixed point method works. So you can see it's very like actually the dynamic user equilibrium. When you solve it, you start with the dynamic loading equation, which is the continuity equation in our case. Then you can solve the traffic density on each link, each segment. And here we also have queuing size and each node. Then based on these two states, one is on the link, one on the node, then you can solve route choice behavior based on complementarity condition and also speed choice based on the HJB equation. So once you have these two, then the route choice give you a turning ratio at each node, and speed choice give you the driving speed. Then you can feed back to dynamic loading problem again, then do it iteratively. So if you block this part, the upper part actually is the how you solve dynamic user equilibrium. So it's the dynamic loading and route choice that's the issue. So for mean-field game, we basically not only model route choice, but also model the speed choice. What the online learning method we present, because I'm running out of time, so I will just quickly give you some idea. So remember, the mean-field game consists of two dynamic. One is the agent, the individual agent dynamic. One is the mass dynamic. So now I discretize time. Now it's not PDE anymore. It's the transition equation. For agent dynamic, it's the transition equation from Q at time t to Q plus t time t plus 1. So once the agent pick an optimal control strategy, is state update based on some transition. And the mass dynamic follow also a discrete transition equation. So this is PI is a fixed point model. So you start with some initial guess for density, and then you solve the U based on the HJB equation, and then basically you solve optimal U based on the row 0. And then once you solve U, then you solve FPK, which is also optimal density to fail. Given that U, then you do this iteratively. Many times this may not convert because this fixed point. Sometimes it can basically go, if it's not a descent direction, it can go to some other places. So that's why we developed so-called semi-gradient descent method. So every time we start with the initial row 0, we don't solve the optimal density for the entire velocity. We solve a suboptimal. But then based on the suboptimal, we solve density. So every time we don't do this zigzag too much. Instead, we only solve a suboptimal that actually make sure our direction doesn't deviate from the same direction. Then we can show if it's online learning sampling scheme, which means the car drive, collect the sample and learn based on the reward function. Then they collect more sample, the more they collect, eventually they can actually converge to the same optimum equilibrium, like what we did before. So yeah, I will skip the theory part of this. But we found out that instead of only apply learning to the HJB equation, but we apply learning to both two equations together, we found that the direction is the actual descent. For the fixed point, it's that direction is not descent. That's why sometimes it can go to some other places in search space. Yeah, so we have some theory to support the direction, why this is the descent direction compared to other methods. I will skip here, but yeah, I will want to end my talk with this. So questions, why do we need mean field game for traffic flow? So this actually come to me many times whenever I present this topic, because I think using game theory to model traffic flow is it's uncommon. Normally people just use PDE system, right? So they propose different PDE systems. So this is my argument. I hope my argument can convince partially at least everybody here in the room. So we first show that we can reinterpret existing traffic flow model by a mean field game. So as long as we can find some special cost function, then the solution, the equilibrium solution, turns out to be equivalent to the solution from classical traffic flow model. But keep in mind there are many cost functions we can design for the cars from the designer perspective. But some of them, of course, are not physically consistent. For example, we use some cost function, we found out the cars end up with moving backwards. So we still think it's possible if it's self-driving, right? So as long as that the car can communicate with the car behind the scene, okay, I'm backing up. Say to avoid rare end crashes. I think it's okay, but I think people in this community may not accept it either because it's not physical. It doesn't make any sense. But for some cost function, that's the optimal solution. But assume we have some other physically inconsistent objective function we don't want to include in our control. So what the game theory can do is we can push the boundary of traffic flow, hopefully classical traffic flow model, by introducing more cost function that those cost functions are more physically meaningful, but also include some control strategies that cannot be seen in or solved by the classical traffic. So I think that's the we believe is where the game theory can play a role, because we can play around with these different functions that may generate different traffic flows. Yeah, this is my last slide. So, and what I want to say that, so basically, here I talk about we start from the control problem for individual car, but then since we need to control the multi-agent system, so it ends up with a game theory. It's naturally a game theory framework, but to solve it is not easy. That's why I introduced machine learning speed to solve it. But there are many still open questions. For example, people always ask, if you use mean field approximation, you assume every car is homogeneous. But how do you capture those kind of corner cases if some car behave erratically? And also, so far we still couldn't prove some mathematical properties like uniqueness of the mean field equilibrium, and also some convergence in the algorithms. And also, I think for mean field game, the most challenge here is how do we incorporate the safety aware collision avoidance? Because the car they don't look at the individual car in the neighborhood, instead they look at the traffic density. So then it's very hard to model the car, when they are distantly close, their force between each other is very large, the cost is huge. That's why now we try to use a different set of game to solve it. Okay, so I would like to thank my students, postdocs, and also my collaborators. Yeah, I work actually a lot with the European collaborators. Thank you.
Okay, so questions.
Three questions. So one is on, so did you actually investigate the advantages of your approach for numerical stability? I have the impression that this might be an important feature that might be
Okay, well,
might actually be outperforming like with ambitious models, right?
yes, yes. Yeah, thank you for mentioning that. Yes, we did. We have this linear, we prove the linear stability of the mean field gain. But it's only in the linear sense. We have to basically linearize around the equilibrium points. The mean field equilibrium, and we can show it's stable.
And did you try also under different discretization? Because when you then have to apply it in, I don't know, simulation, etc., maybe in a self-transmission model type, did you actually try and see how much the discretization of the road sections have an impact on numerical stability?
We still have to satisfy the CFA.
Yeah.
Yeah, when we discretize that.
Mhm.
Yeah, I have some backup slides for numerical schemes. Yeah.
And this approach we used the whole link model, like a link transmission model.
So numerically, when we solve it, we have to discretize each
Mhm.
link into small cells.
Yeah.
We haven't tried,
You haven't tried to do
For the
a whole
entire
model.
no.
Would be interesting to see if this could be applied to a link transmission model also for macroscopic analysis, because then the follow-up question is you want to use this traffic flow model, but then you're applying this at a network level,
Right.
right? So in that respect, you're moving more towards macroscopic use of traffic flow models.
Yeah, exactly.
So the follow-up question that I had, or the different question that I had, was more on the assumptions that you're making on the second part, on the network loading. First of all, do you have to know the destination of the flow? So the root choices. If you look at the Price paradox problem, for the solving the Price paradox problem, both entry flows, they should kind of know that the destination is
Right.
the right link.
Yeah,
Right?
exactly.
It has to be known a priori, which means you need to apply it on autonomous vehicles, because in principle you are considering that in the future, basically every vehicle will share what is their final destination.
Yes.
Yeah.
So here we have to know that.
Yeah.
So because we also use link node based formulation. So yeah, you can see we have to attach the destination.
Yes.
Yeah.
Third and last, the beta. You have to, so later in another slide, you show that you have this feedback loop where you have the beta.
To solve it, yes.
Can you actually use different node models for this? Like the turning ratio there is actually calculated based on your root choices. But then every time in a network loading model, the node models can be different depending on the policy within nodes.
Oh, you are saying more like a priority rule.
Yeah, priority rule, especially when you're dealing with highly congestion problems, feedback effect, etc. You know, the Tampere principles of node models.
Yeah.
So in that respect, you need to define what type of priority mechanisms are in there.
Yeah, that is on the top of this. Yeah,
That will be on top
top
of
of
this,
that.
yeah.
Yeah, we have
Okay.
to also apply that.
Yeah, you need to then define what type of node policy is imposed there, and that will be something that you need to assume once,
Prior, yes.
prior, yes.
So, yeah, that's why in the one paper we published, they asked what's the difference between yours and the DOE.
Mhm.
We saying our is actually DOE, but we basically couple both our choices. Yeah, so we call it dual mean field gain. So one mean field gain on link, one mean field gain. Yeah, but they are coupled by the osmolar parts. So we have to learn from those DOE. What the assumption are. To share secret.
Thanks.
Do you have more questions?
When David stood up, I was scared. I have loads of questions.
I probably a little bit lost on this, but. So when you say this is a control. Are you controlling all of the vehicles centrally in your mean field problem? Or are you assuming that each of them is running this control independently, assuming that they have some model of the rest of the world?
Good question. Actually, it's a decentralized. So that's why, yeah,
There's no communication between vehicles.
that's a good question. Actually, they don't how to communicate among each other, but there should, you can assume there is a central
Well, that's the
information
question.
system.
So there is
Yeah.
the vehicle, the infrastructure. The infrastructure is telling the vehicles where to move in order to achieve this, or are the vehicles assessing that themselves? You're
So
calling them autonomous rather than connected, so I'm not entirely clear as to that.
So yeah, so sorry for the confusion here. So what the information they need to know is the traffic density. So they have to have some central information to
Can
draw
they
that.
assess traffic density with sensors on board? If I have a LiDAR on top of my car, I have a reasonably good estimate of
About the
density,
local.
of the local density. Is that sufficient for this?
Yes, but I would say ours is local in space, but global in time. So which means, yes, they just need the local density information, but they have to anticipate what the future density will be like, because others are also playing games.
But if the others are playing. But if everybody's playing games, should the central controller be telling them to coordinate? If you had a central coordinator, that's the point of it, is to tell them to coordinate. Whereas if they're decentralized, then they need to coordinate based on some sort of agreement or logic or commonality of.
Okay, so maybe let's think this way. So, basic mutual equilibrium is an approximation of n-player Nash. So it's still Nash equilibrium.
So that's decentralized.
Decentralized. But they have to be able to to anticipate what the future density is, but that anticipation at the equilibrium actually is aligns with their optimal spread. So
How
that's,
far in the future do they need information in order to do that?
it depends on the planning horizon you define. So the longer, the harder to solve them.
But I mean, there's diminishing returns to time, right? So the first second is more important than the second second, and the second second is more important than the third second. Right, so who cares what's happening a minute from now, because that's too far into the future with too much stochasticity and unpredictability.
So yeah, if that's the infinite time horizon, probably you'll have the weights in front of different time steps. But if it's a finite time horizon and it's not that long, probably we can still do it equally. Yeah, but you can add weights. So theoretically, it doesn't matter because at the equilibrium, so that's the confusion part about how equilibrium is defined, right? Versus the online planning. So online planning, you can do planning horizon, moving window. But for equilibrium, if you think from learning perspective, every time I try to, so for this time horizon, I try to guess what's the future is. If my guess is wrong, then turns out my strategy is not optimal. Then I play again. So then I keep learning, and eventually everybody should be able to learn that optimal. Control strategy that collectively form the inherent traffic density. So that's the physical meaning of diffusion. So the anticipation of the traffic, the density is consistent with everybody's anticipation. So
My final question, because the not limitation, but the assumption is that n goes to infinity. So in very sparse situation, when you have very free flow condition, have you checked that what's the optimal solution?
in free flow.
Almost here, few cars.
Oh,
Is that-
filter. Yes. So because this is a approximation, so very good question. So this is a conclusion actually for general mean field game. So as I mentioned, so you can treat mean field equilibrium as an approximation of n-player Nash equilibrium. So there's a difference when this is the number of agents. If the agent become large, so your mean field should actually more close, equilibrium close to the actual optimal control strike for each agent. But if the engine is small, yes, there's a gap that the scaling factor is 1 over square root. Yeah, but this is a limitation for sure. So that's why this cannot capture the collision weight. Because for collision weight, then we only look at cars in my neighborhood. And so that's why now we go back to the n-player game and try to say, can we just directly solve n-player? Instead of first you need your approximation number.
Okay, great.